Young people, it's Mrs. Rains, and I'm going to be talking about at least two of the four guys' gas laws tonight, and I'll get the other two tomorrow. So first, we want to review properties of gases. There are four quantities that need to be defined when we're talking about gases. That's the quantity of the gas, the number of moles, the temperature of the gas, T, the volume of the gas, V, in liters, and the pressure of the gas, P. And remember, P can vary, whereas T and V and N don't, but P does vary a bit, so we have to make sure we understand that and keep that in mind, that we always have to pay attention to the unit that P is in when we're talking about gases. Okay, so the first guy we're going to talk about is Boyle's Law, and Boyle talked about volume and pressure, and he basically figured out that all gases behave in this manner, and that's one of the reasons why we figured this out, or he figured this out. Things were behaving in the same way, and he was like, something's going on here. So Robert Boyle was an Irish chemist, and he studied PV relationships using something called a J-tube in his multi-story entryway. And most of these guys that were chemists at the time were actually really rich guys. They actually had money, they were usually titled, and they had time on their hands. So this is what they did. And they were pretty smart cookies too, if you ask me. So here's a picture of Robert Boyle. Yeah, he was fancy. And these are the J-tubes. Now, his J-tubes were much larger than the ones shown over here. And it says to the right because it's to the right on your notes, but it's to the left here. Okay? So we see that when we start plotting pressure versus temperature, we get in A this really funny line that's curved. It's got an exponential kind of curve to it. But there's a problem. Chemists don't like curves. We like straight lines. We like things that are very predictable. So what we can tell from the curve is that pressure is proportional to 1 over volume. In other words, it's inversely proportional. So as pressure goes up, what happens to volume? Volume goes down. As volume goes up, pressure goes down. Vice versa. It's an indirect relationship. So as one goes up, the other goes down, versus as one goes up, the other goes up. It's a little different. Also remember that this is constant temperature. Now it doesn't say constant moles because at the time they didn't know anything about these quantities of particles. They didn't know anything about moles or atoms or molecules. They were just looking at gases. They were just looking at things like volume, pressure, and temperature before they even knew anything about that. So for a given quantity of gas at a constant temperature, the product of the pressure and the volume is constant. So pressure times volume is equal to some kind of constant, which means that volume is equal to K divided by P, or K times 1 over P. And so we get this idea that somehow, if we look at this relationship, volume is equal to K times 1 over P, volume is equal to I, and X is equal to 1 over P. The intercept of the line is 0, B. So this is the data that Boyle originally collected and graphed when he actually did his experiment. And so this is what the significance of this data is. This is Boyle's original data, and we can see that it works out very well. And as chemists, we do everything we can do to get straight lines. So you'll notice what we kind of end up doing is taking P, dividing it by 1 over P, taking 1 divided by P, and we get this quantity that then we graph versus V, and we get a straight line, which means that the constant K is the slope of the line. And we can predict a whole lot of things from that. And so that's going to be a really important factor all throughout our school year here, is that when we have curved lines, we're going to do things as chemists to try to figure out how they're straight. And that's going to come into play a little bit later when we are in our kinetics portion, okay? So we'll talk about that a little bit later. This idea of curved lines going straight and how we figure that out. But ultimately what you need to understand is that this relationship of V and P is indirectly related, okay? So Boyle's Law. The easiest way to remember this is P1 times V1 is equal to P2 times V2. That's the easiest form of Boyle's Law to memorize, okay? Boyle's Law has been tested for over 3 centuries, and it holds true only at low pressures. When we start getting to super high pressures, things get a little weird. So think about the pressures that we live in. Think about the pressures that we can create with our hands. Those are the kind of pressures we're talking about here for Boyle's Law. When we start creating different pressures with different things, we get a little hinky, okay? So we can see here when we graph volume versus pressure, we get a very exponential decay line. We don't really like those as chemists, so we will do things to try to figure out how to get around that, okay? And you will also notice here, see, when we add more mass, do you see a 1 kilogram mass on the left and a 2 kilogram mass on the right? When we add more mass, that means we're adding more pressure to that container, therefore squeezing that gas into a smaller space. Because the pressure is greater because there's more force in the same area, the pressure gets greater and the volume divides in half. Okay, so that's kind of the idea that you need to remember. And the easiest formula to remember is P1 times V1 is equal to P2 times V2. That's the easiest Boyle's Law to remember, okay? So, sulfur dioxide, SO2, a gas that plays a central role in the formation of acid rain, is found in exhaust of automobiles and power plants. Consider a 1.53 liter sample of gaseous SO2 at a pressure of 5.6 times 10 to the third PA. If the pressure is changed to 1.5 times 10 to the fourth PA at a constant temperature, what will be the new volume of the gas? Again, I need you to bring back your ideas, answers, and questions tomorrow for this problem. Try it out, bring back your ideas, okay? 2 is a little different. So you have to kind of do a little graphy graph here. And then you've got to work backwards to account for the trend that you see and try to figure out how to develop that trend during this data and explain it, okay? So this one is a little beyond where we are right now, so we'll probably be coming back to this later, so don't worry too much about exercise 4, but I do want you to try to graph it and see what kind of graph you get, making sure that it comes out to be the same kind of graph and getting the idea of what the relationship between P and V is. And what happens if pressure goes up? What happens if volume goes up? What happens to the other, one and the other, okay? So next one is Charles' Law. Charles' Law is that if a given quantity of gas is held at a constant pressure, so pressure doesn't change, then volume is directly proportional to its temperature, okay? This is a problem. So it says, why must we use kelvins? Got to use kelvins, why? And it really comes down to this one thing. What's the smallest volume that we can have? If you said 0, you would be correct. But if we're using Celsius, we can get negative temperatures. If we have negative temperatures, that would imply we could have negative volumes. And that just can't happen. So it is very imperative that if you're doing any gas law problem at all, Charles, Boyle's, any of the 4 guys, or any other gas law, you need to change temperature to Kelvin, because this is what is going to correct for the idea that Celsius scale can be negative, but we can't have volumes that are less than 0. So that's going to be a really important factor, and that's what happens. So if you think about a balloon, I can't have a balloon that has less than 0 volume. It either has no volume, 0, or it has volume. It doesn't have less than 0. It can't suck in on itself. So we got to make sure that that's taken care of. So Jacques Charles was a French physicist, and he was the first person to fill a hot air balloon with hydrogen gas and fly the daggum thing, okay? So he was kind of intrepid, and you'll also have to remember that many of these guys were working at the same time. Irish and English were a little bit formal, the French were a little bit informal, because you got to remember this is kind of French Revolution-ish. So these guys were not trying to be formal at all because they didn't want to be mixed up with the Louis and the Marie Antoinette scandal, because nobody wanted to lose their head. Okay, so Charles' Law says that volume is proportional to temperature and that it makes a straight line plot. So if you look at the graph that I just put up, there are several different substances that are graphed. And you will notice that every single one of those graphs of temperature, or volume versus temperature, temperature as the x-axis, volume as the y-axis, all make a straight line. This is chemist approved right here. Chemist approved, straight lines, chemist approved. What we find is that temperature is directly proportional to volume. So that means as temperature goes up, volume goes up. As temperature goes down, volume goes down, and vice versa. And this is going to be a really important thing. So the one that I knew growing up is V1 over T1 is equal to V2 over T2. But a lot of times we try to make it all look the same. I find that V1 times T2 is equal to V2 times T1 is confusing because we're mixing numbers up. So I still remember V1 over T1 is equal to V2 over T2. It's just something that I've always had in my brain since first year chemistry when I was 14 years old. Either one works because it's actually the same equation. If you look at the algebraic math and the algebraic rearrangement, you will see that clearly. But please make sure that you have an idea of that understanding. Notice pressure is not included here. Why is pressure not included? Pressure is not included because pressure is constant. It doesn't change, so if it doesn't change, it remains constant everywhere. So this figure on the side shows a graph of volume versus temperature. We just talked about that. And you will see that the solid lines represents the experimental measurement on gases, but we can extrapolate. That means go beyond the data and draw a line, and the straight line leads us to a point, and it's called the absolute zero temperature. And that's how absolute zero was actually developed. It comes from these graphs and the point at which temperature doesn't change anymore and volume doesn't change anymore and all that good wonderful stuff where everything kind of comes out to be a 0 point. The dashed line represents the extrapolation of the data. Note the samples contain different numbers of moles. You'll see N is different on each of them. It doesn't matter what the N is. As long as pressure is held constant, this will always happen. Now you will notice that the slopes of the lines are different because the N's are different, but the relationship is still the same. Volume and temperature are directly related. So what is the temperature when the volume extrapolates to 0? Yeah, 0 Kelvin or negative 273.15, which is absolute zero. Okay, so example of Charles' law. A sample of gas at 15 degrees Celsius and 1 atmosphere has a volume of 2.58 liters. What volume will this gas occupy at 38 degrees Celsius and 1 atmosphere? Again, problem number 6, like problem number 4, I think, is a problem that I want you to bring back to class. The first Boyles Law problem and this problem I want you to bring back to class tomorrow with some solution. Okay? So, talking a little bit more about Charles' law. Each of the balloons below contains the same number of particles, so there are the same number of particles in here. But if I heat them up, I speed them up, and if I speed them up, then they gain more kinetic energy, moving faster, colliding with the walls of the container, and if the walls are made of rubber or they can expand and contract, it gets bigger. Okay, if the walls can't expand and contract, then we have a different situation because no longer can volume change. And so we'll be talking about that a little bit more tomorrow, okay? Thank you so much for tonight, and I will see you tomorrow.